Alright, so our answers here on part A, you should have gotten the time equal to negative 1/5, okay? And that gives you vector PR equal to negative 6/5. Negative 6/5. And then the vertical component was 3/5. Okay. Then you find the magnitude of that to find that shortest distance, and that comes out to 3√5/5. Okay. So 3√5/5. Okay. So that's part A. Part C. S, our time was negative 1/2. That gave us, I made, since they gave us point R, and we've been using PR, I made the other point P. So vector RP would have been 4.5, 4.5. By the way, don't worry about, oh, did I get them in the right order? Because we're just looking at we don't really care about the direction. All we care about is that distance. So even if I had done PR and gotten negative 4.5, negative 4.5, I'll still get the same magnitude. Okay? So then we have the magnitude of RP equal to 9√2/2. Okay. So, did anyone have any questions about any part of those?
When you plugged in the S into the PR or RT.
Yes.
5 plus 1/2 and the 5.
Well, it's a negative 1/2. Yeah, S was a negative 1/2. That's why 5 plus a negative half is 4.5. 4 minus a negative 1/2 would be 4 plus a half. Anything else? Alright, I want to look at another application, and this is when we're not given an equation for a line. We have to come up with the equation first and then kind of go through this process. And then also I want to explore a little bit with 3D vectors, okay? Well, let's start out here. What if we're not given the equation of the line? It says, on the map shown, the distances are measured in kilometers. Ship R is moving in the direction 3,4 at 10 kilometers per hour. It says, write an expression for the position of the ship in terms of t, the number of hours after leaving port. Okay? And then secondly, find the time when the ship is closest to port P, which is at the point 10-2. Now, what's challenging about this one, and it's really easy to overlook, is the fact that we were given a direction vector and we were given a specific magnitude, that 10 kilometers per hour. Okay, and if you recall before we left for break, we talked about how to get a certain magnitude in a particular direction. Okay, does anyone remember how to do that? Yeah, using our unit vector. Okay. So, this vector 3,4, we could check, but unless it actually has a magnitude of 10, we're going to have to do something to it in order to get it to be the velocity vector for ship R. Does that make sense? kinda. Okay. So now, what is the magnitude of this vector 3, 4? It's 5, okay? Might recognize the Pythagorean triple, 3, 4, 5. So the magnitude of this is 5. So what do we need to do to this direction vector to get it to be a velocity vector? Okay. What do we have to do to that?
Multiply times 2.
Yeah, multiply it by 2. Remember when we talked about constant multiples way at the beginning in chapter 12? We said if you multiply a vector by a constant, it will multiply the magnitude by that same constant. Okay? Remember we did this, C, V, okay? If the magnitude, if we multiply a vector by a constant, then the magnitude will be multiplied by that constant as well. So we see here, hey, our vector or our direction only has a magnitude of 5. I want a magnitude of 10, so I'm going to multiply it by 2. So what's my actual velocity vector here?
6, 8.
Yeah, 6, 8. Okay? 6, 8. Does that part all make sense?
So does that make 3 for the position vector?
No, the position vector they gave us over here.
Oh, it's A. Okay.
Yeah, that's point A. We want this ship to start at A and go at this velocity. Okay? So, for part A, write an expression for the position. I'm going to make xy equal to our starting position vector, negative 8, 3, plus t times our velocity. And make sure you use the 6, 8. Otherwise, your ship will only be going 5 kilometers an hour instead of 10. Okay? So that's part A. Are there any questions about how we got that equation? Alright, so here we are over at port P, and we have something to deliver to the ship. Okay, we don't feel like driving all the way around, so we're going to try to meet it, but we don't want to travel any further than we have to. Okay, so we want to figure out what that shortest distance is, and again, they're looking for a time when the ship is going to be closest to that port. So here we're actually going to find it's not just the distance that we're looking for the time. Okay?
Well, that
And
makes it
so
easier.
actually it's a little bit shorter of a problem than originally. Okay? So for part B, we're going to do just like what we were doing in the previous steps. We need to define this point R in terms of the parametric equations. Okay? So what would that be?
-8 plus 6t and 3 plus 8t.
Yeah. Okay, use the parametrics for that vector equation that we got in part A. The horizontal components, -8 plus 6t. So this, when we're finding point R, we're really kind of finding a position vector to that spot, okay? Using the parametric equations. So now we want the vector from P to R. So -8 plus 6t minus 10 is -18 plus 6t. And 3 plus 8t minus 2 is 1 plus 8t. Okay? So where do we go from there? Dot product equal to 0, okay? And by the way, you can use the velocity or you can use the direction vector because those are parallel. So when you find the perpendicular, it'll be the same either way. Since I've got it here, I'll go ahead and use v dot pr. Alright, so 6 times -18 plus 6t, that's going to be a negative 108. Yeah, negative 108 plus 36t, and then plus 8 times 1 plus 8t, so 8 plus 64t.
Wait, did you do 6 times 8 is 108?
6 times 18.
Okay.
Yes.
For PR, what did you subtract?
I did, I'm going from point P to this point R that we came up with.
Oh, so with 10 and 2.
So yeah, -8 plus 6t minus the 10, and then 3 plus 8t minus the 2.
Use that.
Alright, so we want where that equals 0 to get it perpendicular. We'll simplify. Here's a -100, and that's a 100t. Oh, that's nice. So t equals 1 hour. So 1 hour after the other ship leaves, it'll be the closest point to the port P. Okay. So knowing that if you're at port P and you know it's going to take you 2 hours to get to that spot, you need to leave an hour before you know the ship up at the first port is going to leave. Okay. You can figure out when you would need to leave in order to minimize your distance to meet them there or something like that. Okay? We could go on and find what that actual distance is, but we don't have to in this case. Okay? Alright, so we've done a few of those. Notice again, this is just an extension of what we were just doing. Let's take it one step further and let's look at three-dimensional situations. Okay? Three-dimensional situations. And this is taken actually directly from the homework section in your book, but number 6 says, find the coordinates of the foot of the perpendicular from the point 3, 0, -1 to the line with parametric equations. X equals 2 plus 3t, y equals -1 plus 2t, and z equals 4 plus t. So, what do you think we could do with this?
Get R.
Okay, get R from the parametric equations, okay? So what's R?
X, Y, Z
Yeah, okay. 2 plus 3t, -1 plus 2t, and 4 plus t. Okay, very good. Alright, what's our next step?
You subtract the original point from each of those.
Okay, and we'll
So,
call
like-
it P.
So like 2 minus 3 plus t
Okay, good.
should be
Yeah,
negative 1
2
plus 3t.
minus the 3, -1 plus 3t.
And then because the next one's 0, that would just be the same.
Okay,
And then minus the -1 would be 5 plus t.
okay, good. Alright. So notice the process is the same, like so many of the things that we've done with three-dimensional vectors. You're doing the same process, you just add in that third component. Okay? Whatever you're doing with the first two components in 2 dimensions, you do with the third component here. Okay?
And then you do the same thing. You find the dot product of the velocity vector and PR and set it to 0.
Okay. Now, what is the velocity vector in this case?
3, 2, and 1.
Good. Yeah. 3, 2, and 1 is our velocity.
Did we get that from, oh.
Yeah, we got that from our parametric equations. So whatever you're multiplying the t by is going to be that component of the velocity vector. Alright, so yeah, now we're going to do PR dot V. And we want it to equal 0, okay?
Plus 9t, -2 plus 4t, and 5 plus t. Add them all up. -5, 0, plus 14t equals 0, so t just equals 0. That was easy.
Yeah.
What does that mean exactly?
So
It
the
means it's
closest, the
already
shortest
perpendicular.
distance from the point
It goes through the point is what
to
it
the
means.
line
Is the point
is what point?
P.
the starting point?
The starting point, which is what in this case?
P.
No?
2, -1, 4.
Ah, there. 2, -1,
Oh.
4.
Oh, okay.
The shortest distance is when time equals 0. That's 2, -1, 4. Okay. So the moment this thing starts moving, we're further away. Okay? Now, they're not always going to turn out, have time equals 0, obviously, but whatever the time is, you could then go and plug that in, okay? Now, the one thing we did not do is actually answer part A. Okay, we answered part B.
Find the coordinates of the foot, so then we just have to, well, didn't
2,
we just,
-1, 4.
did we just do that though? Isn't that the 2, -1, 4?
That is, well, no, the foot of the perpendicular,
Is R the one?
Well,
oh,
isn't
wait,
that what
hang on,
it
hang on.
Are we
Sorry.
using-
Yeah, we did just do A, sorry. We need to do B, find the actual distance. Sorry.
So then you just, the distance would be,
Whatever root 21 is.
Where you get root 21.
Now it makes more sense.
2 squared plus 1 squared plus 4 squared. Square root of that.
Not quite. What do we want to find the magnitude of?
PR, so it'd be, you plug that 0 in and you get -1, -1, and 5, and then it would be 25 plus
Oh, yeah, we did
2
that.
would be the square root of 27,
Yeah.
which would be 3 root 3. Did I do that right?
Square root of 27 would be 3 root 3, yeah. So,
That's not enough.
so that's your shortest distance. 3 root 3. The foot of the perpendicular is 2, -1, 4. The shortest distance is 3 root 3. Okay? Is that pretty clear?
Yeah.
So you'll notice we're really not doing anything different than what we did in the first example. Each problem just has a little nuance to it or a little extra component, or in this case, a third dimension that we have to deal with. But it's all basically the same process.
Is it gonna be like that with each dimension we go You used to add another.
I haven't really looked into it. Because vectors are so tied to the real world, I mean, we don't really get up into more dimensions. I mean, we're already in the real world here. We have,
That's pretty low. That's pretty
well, time is our fourth dimension here, yeah. So we're in three-dimensional space with time, so we're dealing with 4 dimensions here. I don't know what the 5th dimension would be or anything like that, but, okay. So, I gave you a few of these to practice with, okay? 2, 3, 4, 5, and 7. Some of these are similar. Each one has a little extra component to it to work with. Here, you're actually looking at 2 different boats traveling rather than just a point to a point. Finding the angle between paths. This is kind of a throwback to stuff we did earlier. And then here, at what time are the boats closest to each other? So, well, if you do that, I mean, that would be one thing. If they're going to be closest together if they collide with one another. But my assumption is here that if you did that, you'd probably get a negative t. Okay? So, you'll need to look at the paths. That's one where maybe sketching it would be helpful. Okay?
Right, because because they might go through the same point, but they're not necessarily going to go through it at the same time. Whereas if you just set the parametric equations equal to each other, you get what point that is, but you miss out on the actual time they would each there.
Mm-hmm.
It should make 'cause it's-
Yeah. So, and then here's another one with 3D you could try as well. Okay? Alright. So that's it for